Section 7.8, acid-base neutralization reactions. I'll go a little quick on this because we talked about some of this last week. We recognize acids as having formulas that start with hydrogen. There's actually multiple definitions of acids, but one of them is that acids tend to form hydrogen ions in solution. Acids tend to taste sour. That sour taste on the outside of like Sour Patch Kids is citric acid. So that's what acids taste like. Lemons and limes get their sour taste from citric acid as well. Acids can dissolve some metals. And then there are bases. Bases tend to form hydroxide ions in solution. And we're going to learn to recognize those as being metal hydroxides. So NaOH or MgOH2. If you see a metal ion and OH, think, okay, that's probably a base. Bases taste bitter and feel slippery. Bases are more hazardous than acids are in general. So here's a table with some common acids, and again, looking at the formulas, we see that all the acid formulas start with H. The base formulas, we have metal, it starts with a metal, and then the last part is OH. So you could recognize those. The names are, whatever metal hydroxide. So we have reactions between acids and bases, and we call those acid-base reactions. They're also called neutralization reactions because acids and bases neutralize each other. When you get an acid reacting with a base, you always get the same general product, which is water and a salt. And by salt, we mean any ionic compound. So it's not just table salt. So let's look at how this happens. We can think of this in predicting products, we can think of it like we did with the precipitation reactions of these things swapping partners. So acids are not ionic compounds, and yet they ionize when they're in water. And so HCl is going to form H plus ions and Cl minus ions when you dissolve it. And sodium hydroxide is soluble and will form sodium ions and hydroxide ions. So these two couples go to the party and then they mingle. And so we're going to look at the combination of sodium and chloride and the combination of hydrogen ion and hydroxide ion and see what's going to happen when those two meet. So we're going to swap the partners. So over here, we're going to try out H plus with OH minus and Na plus with Cl minus. Na plus with Cl minus, plus minus, you just push them together, that's sodium chloride. Sodium chloride is table salt, it's soluble in water. The formula is NaCl. That is what we in everyday life call salt, but if it was potassium chloride or potassium sulfate or something, in chemistry we would also call it salt. So the salt is any ionic compound. Now when we take H plus and OH minus and put those together, we've got plus 1 minus 1. If we just shove them together, we get HOH, which looks a bit strange. So what if we put the two H's together? That's water, H2O. So this is a swapping partner type reaction, and we'll learn at the end of this chapter that that's called a double displacement or a double replacement type reaction where you have ions switching partners. There's no precipitate in this type of a reaction, but we form a liquid. We don't just have two aqueous substances form, two salts form. We have a liquid form. So water is a liquid at room temperature, and it's that forming of that liquid that drives this reaction.
And AQ means that it's dissolved in water, right?
Right, AQ means dissolved in water. Water is not AQ because water doesn't dissolve in water. Water is water, right? It is, yeah. Water is water. It's one of the most profound things I've said lately. If we look at that reaction, that equation, and write a net ionic equation for it, we will always end up, for acid-base reactions, we're always going to end up with the same net ionic equation. and that's this guy right here. The sodium ion and the chloride ion were spectators. It was hydrochloric acid and sodium hydroxide. But the sodium ion and the chloride ion didn't participate in the reaction, only the hydrogen ion and the hydroxide ion. So all acid-base reactions come down to hydrogen ion from the acid and hydroxide ion from the base combining to form water. And so the pattern of this reaction is acid plus base yields water and salt. So here's an example. Write a molecular and net ionic equation. Fro the reaction. Yeah, good typo. Tempted to go fix that, but I won't. For the reaction that occurs between aqueous sulfuric acid and aqueous potassium hydroxide. Okay, so we're given the formulas for the reactants. We've got H2SO4, and that's aqueous. And we've got aqueous potassium hydroxide. And we're supposed to predict the products so that we can write an equation for this. So we look at those and we see H2 starts with H, that's an acid. And we see KOH, that's a base. What if we didn't recognize that those were an acid and base? Well, we could treat this like the precipitation reactions that we've done before and just try swapping partners. And that's going to get us the right answer even if we don't think of it as a neutralization reaction. So I'm going to recommend that you follow those same steps that we did for those other reactions and write the ions below their formulas. So sulfuric acid, we're going to have hydrogen ion and sulfate ion. Sulfate is 2-. And potassium hydroxide is going to dissociate into potassium ions and hydroxide ions. Remember that when a compound ionizes, it forms 2 ions. So don't try to tell me that there's K plus ions and O2- ions and H- ions. Don't get creative like that, okay? Save that for some other class. So we're going to take these guys and we're going to swap partners. And here we've got the H plus with the OH minus. And we've got the SO4, 2-, and the K plus. So the H plus and the OH minus are going to make water. And the state of water is a liquid. K plus, SO4, 2-, we need 2 of the potassiums to balance the charge. I ran out of space. Usually in these neutralization reactions, the ionic compound, the salt that's formed, is soluble. But we could go back and look at the table and see that potassium compounds are generally soluble, sulfate compounds are generally soluble, so this is going to have the state AQ. And then we have to balance this. Any questions about how I got those products? This is really similar to what we did before.
What happened to the second H from the H2SO4? Is that what the balancing is about?
That's what the balancing is about, yeah. So we just swap the ions and we use the charges on the ions to make the formulas. And then we use coefficients to balance it out because now on the left side we have 2 hydrogens in the sulfuric acid and 1 in the potassium hydroxide. That's a total of 3 hydrogens. But on the right side, we only have 2 in the water. And so somehow a hydrogen ion or a hydrogen atom disappeared, and that's not possible. So we're going to have to fix that. So you may look at that and you think, okay, that's kind of messy because there's hydrogens in 2 different places on the left, and I'm not exactly sure. I don't want to deal with that yet. So skip that one. Do something that's easier. Notice that this sulfate ion stayed intact, didn't it? It didn't come apart. So we can balance that as a unit. We've got 1 sulfate on the left and 1 sulfate on the right. So that's okay. Oxygen's kind of all over the place. Let's not mess with that one. How about potassium? There's 2 on the right and 1 on the left. So if we put a 2 here, we'll fix the potassiums, right? Now we're kind of forced to go back and look at either the oxygen or the hydrogen. Well, let's look at the hydrogen. Well, we've got, I need a pointer. We've got 2 hydrogens here, and now we've got 2 over there, right? And over here we only have 2. So we have 4 on the left and only 2 on the right, so we need a 2 here. So we've checked out potassium and sulfate and hydrogen, and now we need to go double check that the oxygens are going to be okay. You can include the oxygen and the sulfate if you want to. I'm not going to because I already looked at that and that was fine. But here we have 2 KOHs, that's 2 oxygen atoms in here, and over here we end up with 2 water molecules, and that's 2 oxygen atoms, okay? So that's our balanced chemical equation. Any questions about that?
So you don't have to count the oxygen that's in the SO4?
You can do this one of 2 ways. You can either look at the elements individually, or you can treat polyatomic atoms that don't come apart as a unit and consider those. So there was SO4 on the left, and there's still SO4 on the right. So I can count that as a unit if I want to. You should come out with the same answer either way, because if we count all the oxygens, we see that there's 4 oxygens here and 2 there, so that's a total of 6 oxygens on the left. Over here on the right, we've got 4 here and 2 there, so that's 6. So whichever makes more sense to you. I find it easier to just see those groups. I think in math in elementary school they call that chunking or something, where you look at chunks of things. It's a little faster. It's not math, it's words. They're talking about chunks of words. That's what it is. I haven't looked at my kids' homework enough. Yes?
So does that mean for this reaction to take place in real life that you would need 2 molecules of the KOH?
Yes. Yeah, it would take 2 molecules of KOH to neutralize or react with 1 molecule of sulfuric acid. Yep, good question. So we get that balance, and now it's asking for the net ionic equation. So there's 2 ways you could do this. We're going to do it the long way. You could say, well, that's a neutralization reaction. All neutralization reactions have the same net ionic equation. It's H plus OH minus gives water. Or we could actually do it. So we're going to do it just to show you. So in doing it, I'm going to erase a little bit here, give myself some space. The way we went about doing net ionic equations is that we first took anything that was aqueous and separated it into ions, and then we looked at the things that were not changed, the spectator ions, and we said, okay, we're just going to get rid of you because you didn't actually do anything. You were just watching. So sulfuric acid has 2 hydrogen ions and 1 sulfate ion. And 2 potassium hydroxides, those are both aqueous. That's going to give us 2 K pluses and 2 OH minuses. And we've got 2 water molecules. We're not going to separate that because that's a liquid. It's not ionized. And over here we've got 2 K pluses, and I ran out of room, and 2 SO4, 2 minus. So anything that was aqueous, I separated into ions. If it's a solid, a liquid, or a gas, you don't separate it. And I'm going to look and see what's going on here. I have 2 potassiums on one side and 2 on the other. Nothing happened to potassium. He did not meet the love of his life or anything like that. And sulfate, I have sulfate here and sulfate there. Nothing happened to the sulfate. So what do I have left? I'm going to write that down. I've got 2 H plus and 2 OH minus, giving 2 H2O. And there's my net ionic equation. Is that the best one we can write?
Yeah, you can divide out into 2.
We can divide all the coefficients by 2. So I'm going to cross those out. And there we get it. H plus OH minus gives us H2O.
So it is
you say this earlier, but to just reiterate,
Mhm.
the only product of these reactions is water and then the salt.
Right.
Okay.
Yeah, in a neutralization reaction, the only product is water. Like, well, what about those other ions? Well, they were floating around in solution to start with, and they're still floating around in solution.
It's not reactive.
It was not a chemical reaction. There's a physical change because you mix them together, but there's not a chemical reaction. The hydrogen ions and the hydroxide ions underwent a chemical change. They were floating around as ions before, and now they are together covalently bonded as water molecules.
So the acid and the base just create water?
Yep. If you have an equal amount of hydrogen ion and hydroxide ion, you end up with water and you get a neutral solution. So like in the lab, if we spill acid on the floor, or actually if we spill acid anywhere, we take baking soda and sprinkle it over the acid. And you can try that at home, mix baking soda and vinegar, and you'll see a lot of fizzing and bubbling, but the sodium hydrogen carbonate is neutralizing the acetic acid in the vinegar. The bubbling is because of a side reaction, which we'll learn about in a few minutes.
So the hydrogen comes out of an ionic bond and then forms a covalent bond then?
Yeah, the hydrogen ion and the hydroxide ion are forming a molecular compound, not an ionic compound.
There's no metal.
There's no metal. And you know, I understand that some of that's like, okay, there seems to be some exceptions there.
Sometimes it can form ions without metal, can't it? Hydrogen?
Well, there are molecular compounds that ionize in water, and acids are examples of that. Hydrochloric acid is not an ionic compound. It's a covalently bonded compound between hydrogen and chlorine. But when you put it in water, it ionizes. And for the purposes of this class, that's a mystery that we're not going to investigate. There are some things that you don't really want to know about yet. You do. Well, that's why you're going to take more chemistry classes. So any questions about this? Now, I didn't write state symbols in my net ionic equation there. Does it matter? Well, as you understand, it matters a great deal to mastering chemistry, right? Mastering chemistry cares, okay? If it says include state symbols, by golly, you better include the state symbols, okay? Pardon me? Lowercase, yes. Lowercase l, lowercase s, lowercase g, lowercase aq. And I know that's really irritating at times, but there are a lot of situations in life where details matter as well. And so just think of it as practice for the rest of your life. You know, like my kids always used to get upset, well, why do I have to show my work? I got the right answer. Well, when you do your taxes, if you just come up with the right amount that you owe the government, they're not so impressed with that. They want to see your work. They want all those stupid worksheets with all the numbers filled in the right places. Don't get the decimal point in the wrong place. They care, right? And so I could give you lots of examples like that. But there are times in your life when you have to pay attention to details. And part of the trick is knowing the difference, because there's other times when details just really don't matter. But when it does matter, you have to be able to take care of the details. So I'm teaching you a life lesson. I can spin anything. I'm serious, I can.
Yes.
So this is also included in section 7.8, gas evolution reactions. Sometimes when you mix two compounds, you get a gas that's formed. Sometimes you see this, like I mentioned with the vinegar and the baking soda, you see bubbling and foaming, or you hear fizzing. So sometimes you can really see the gas. Other times the gas is released and it may be difficult to detect. Sometimes you can detect it because there's an odor present that wasn't there before, and that's from the gas. So some of these are called gas evolution reactions because they evolve a gas. Cryptic names we have for these things. So some of them, like this one, are going to produce a gas directly. If you mix sulfuric acid with lithium sulfide, you get hydrogen sulfide gas, which smells nasty. It's one of the components of rotten eggs. And you get lithium sulfate. And so this gives off a gas directly. Others will give you an intermediate product that decomposes into a gas. And so here, if we have hydrochloric acid and sodium hydrogen carbonate, which is baking soda, when you react this acid with the sodium hydrogen carbonate, you get carbonic acid forming and sodium chloride, but the carbonic acid is not stable, and it decomposes into water and carbon dioxide. And so that's the fizzing that you see. And one of the reasons that you use baking powder or baking soda in baked goods is because it causes that fizzing, and that causes the baked product to be lighter because the gas helps to spread it out. So we're going to learn that there are basically four types of reactions in this class that are going to give off a gas. If you have a reactant that is a sulfide, there's a good chance that you're going to get hydrogen sulfide gas given off. That's going to be really stinky. If you have carbonates or bicarbonates, and again, bicarbonate is another word for hydrogen carbonate. So sodium hydrogen carbonate is baking soda. Sodium carbonate is what we call washing soda. But both of those, as a product, they're going to give us carbonic acid. The carbonic acid is going to decompose into carbon dioxide. If we have sulfites and bisulfites, sulfite is SO3 2 minus, bisulfite is HSO3 1 minus. Those are going to generate hydrogen sulfite, which will decompose into sulfur dioxide gas, which also doesn't smell good. Generally, anything involving sulfur is not a good smell. Ammonium. If you have ammonium ion, you can end up getting ammonium hydroxide, which will decompose and give you ammonia gas. Ammonia gas also doesn't smell good. So there's lots of things that just don't smell good. Well, yeah, but, lots of things are lethal. Water's lethal.
Yeah, at ridiculous concentration.
Well, yeah. But you can drown in like 2 inches of water. So that's not a ridiculous amount. Yeah, it's just
So dangerous.
Okay, so here are examples of these equations. So if we mix hydrochloric acid with potassium sulfide, again, you can predict the products by just exchanging the ions. These things ionize in solution. They have AQ. So we switch the partners and we end up with H2S. But then you need to remember, oh, that's a gas, okay? And the other product is potassium chloride. Mixing hydrochloric acid with potassium carbonate. So if we switch the partners, we're going to predict that we get hydrogen ion and carbonate ion. So then that would give us that hydrogen carbonate, but then we have to remember, oh, hydrogen carbonate comes apart. Let's actually draw that. So I don't think that's on here anywhere.
Do we need to memorize this table, or will you give it to us?
Yeah, you need to know this table.
How do we know that HCl and K2S become a gas? Is that just memorization?
The H2S, you have to remember that.
Okay.
So that's carbonic acid. And so what happens is you get water. So all of these guys, the carbonic acid or the H2CO3, hydrogen carbonate, hydrogen sulfite, and ammonium hydroxide, they all give off water. So you exchange the products and you see, oh, I got H2CO3. Oh, I think that was one of those ones that comes apart. Darn it, I can't remember what it comes apart into. Pull water out of it and see what's left. So pull water out of it. If I take the H2s out and one of the O's, what do I have left? CO2. Is carbon dioxide a gas? We should all know that. Okay, and same thing with the H2SO3.
It's chill.
H, that's, what am I doing? H2SO3. Well, pull the water out of it. What's left? SO2. Now that might be a little harder to remember that that's a gas. And let's find another little space over here. NH4OH. I'm going to go down. Well, what happens if we pull water out of that one? H2O, and what's left? NH3. Ammonia is a gas. Now, you may have used ammonia, or your mom may have used ammonia in cleaning the house. What she used was a solution of ammonia, a very dilute solution of ammonia, because pure ammonia is a gas, and Wyndham is correct that is lethal. You know, if you just took a big whiff of ammonia, I'm pretty sure it would kill you. But you're going to have a hard time getting your hands on pure ammonia.
Does ammonia mix with something else that makes like F gas or something?
Well, you have to be really careful with household cleaning, which, you know, may be a reason just to not clean anymore, to mix ammonia with anything containing bleach.
Oh, my mom did that, it was horrible.
Yeah, that will create a very toxic gas and can also cause your toilet to explode. Yeah, it can explode. Yeah. Well, see, I saw this and I'm like, oh, that's so tempting. They say the definition of insanity is doing the same thing over and over again and expecting a different result. So then cleaning the house must be insane, right? Because I keep doing the same thing over and over again and I'm not getting anywhere. So why do I even try it anymore? And yet you just really can't live like that. Anyway, when you get a reaction and you have one of these as the products, you need to well, none, that guy. You need to recognize that the H2CO3, the H2SO3, the NH4OH, that those are going to decompose. They're going to form water, and whatever's left is a gas.
Good
Yes.
question. So, to remember that SO2, would SO2, SO3, and SO4 all become a gaseous state?
No. Only the H2SO3.
Okay.
The H2SO4, if you pull the water off of that, you'd get SO3, and it just doesn't do that.
Okay.
Yes.
So, I'm trying to figure out how they become gases. If there's a diatomic element like the O2, is that what makes it a gas? Just diatomic
No.
element inside the gas?
Good question.
That is a good question. Why is SO2 a gas? Why is CO2 a gas? We'll learn later about something called intermolecular forces, which are the forces of attraction that hold molecules together. You know, that's what's holding the water molecules in my energy drink together as a liquid. Some things have much stronger intermolecular forces than others. CO2 and SO2 have very weak intermolecular forces, so there's nothing really holding them together, and so they just fly apart and they become a gas. If something has very strong intermolecular forces, then it'll be a solid at room temperature. So we'll understand.
Is the only route for like studying for what films become gases? Just kind of
I think with this, you just kind of have to memorize it.
Okay.
Yeah. And I'll tell you that this business right here about the gas evolution reactions, this is not a big deal, okay? This is a small deal. This is I want to get an A, so I'm going to care about this deal. If you're just struggling to pass the class, I give you permission to just kind of gloss over this and give it your best shot on an exam, okay? So, because there's some things that we do in here that I tell you, you know, you really have to figure this one out. Dimensional analysis is one of those. You got to figure it out. It's coming back in Chapter 8. It's coming back. So you got to figure that out. This, if you don't figure this out, you'll be okay. Why do you even tell us about it? It's in the book, I have to. So, instructions, writing equations for gas evolution reactions. Write a skeletal equation, including the reactants and products that form when the cation of each reactant combines with the anion of the other. So we're going to do that partner swapping thing. And then this is the, you know, the tricky part right here. Whoops, wrong color. black on gray. Never works real well. This is the tricky part. Recognize that H2CO3, H2SO, that's a typo, SO3, NH4OH decompose into water, carbon dioxide, SO2, and ammonia respectively. So this is supposed to be a 3. Now it's a 3. So you have to recognize that part and then balance the equation. So I think there's an example coming. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So we have to write the formulas for the reactants first. Hydrobromic acid, that's an acid. It's going to start with hydrogen. The name hydrobromic tells us it's just hydrogen and bromine. Bromine in the periodic table, if it makes an ion, makes a -1 ion, and so it's got 1 hydrogen, and so we got HBr. I know, I forgot to press annotation. HBr, aqueous. And that's reacting with potassium sulfite. Okay, well, I'm going to actually just write these ions down below, since we just talked about what they were. Potassium is K+, sulfite is the light version of sulfate. So it's SO3, 2-. +1 minus 2, we can do that crisscross thing and get K2SO3. And we're told that that's aqueous. So now we're going to swap partners. And we're going to have H plus with SO3, 2-, and we're going to have K plus with Br-. H plus and SO3, 2-, we're going to get H2SO3. K plus and Br-, we're going to get KBr. If you look that up, you'll find out that that's aqueous. That H2SO3, that's where we have to have the little red light go on in our brain. Oh, that's one of those that makes a gas. So instead of writing this, we need to write what it comes apart into. It decomposes into water and SO2. So then I'm going to rewrite this down here. KBr aqueous plus K2SO3 aqueous goes to H2O liquid, SO2 gas, smelly gas, and KBr. And by the way, when you break wind and it stinks, sulfur compounds. Serious. It is. I have 5 boys. It happens a lot, and actually the girl is the loudest. It's horrendous. Okay, so now we've got our skeletal equation here. We have to balance this. This is, we balance by inspection, and once you get a little practice with balancing, then you can just kind of pick out the ones that might be a little easier to balance. And so it's like, okay, bromine on one side, bromine on the other. 1 sulfur, that's okay. I'm going to leave the hydrogen and oxygen to the end because they're all over the place. So potassium. I've got 2 potassiums on the left and only 1 on the right, so I'm going to put a 2 here. That messed up the bromines. So then I have to go back over here and put a 2 there. So now I've got 2 bromines on the left, 2 on the right, 2 potassiums on the left, 2 on the right, 1 sulfur on the left, 1 sulfur on the right. Now let's look at the hydrogens. 2 hydrogens on the left, 2 hydrogens on the right. And let's check the oxygens. 3 on the left and 3 on the right. Perfect. So that's our balanced molecular equation. Any questions?
So we don't have to break down, so the SO2 would no longer be considered we was at a polyatomic listing, and we no longer going to use it as a solid? Or is it
We can't balance the sulfite because on the right side, the sulfite came apart.
Okay.
So we on the right side in the products, we actually don't have sulfite anymore.
Okay, we have sulfur.
Right, and so then you do have to look at them individually.
Okay, so should we just break it apart then, and just like S-2 and,
No,
no?
don't try to break things into ions that are not ions.
Okay.
If you were asked to write a net ionic equation for this, because SO2 is a gas, you wouldn't separate it.
Okay.
You wouldn't separate the liquid either. But they're not asking us to do that, so we're not going to do it.
That's the words we look for to cross out the ones that don't react. Is net
Yeah, if
ionic
you're looking
versus-
for a net ionic equation, you're going to try to find the spectator ions and get rid of them. And just see who was fighting in the boxing ring. And you do that by anything that's aqueous, you separate those into the ions and see which ones are unchanged and cross those out. So we could write a net ionic equation for this one. We should?
It gives more practice on doing a net ionic.
So I'm going to kind of do this in my head.
Okay.
So I see that there's bromide on both sides and that there's potassium on both sides. And so what we end up with here is 2H plus SO3, 2 minus, gives H2O plus SO2. That's our net ionic equation. I skipped the total ionic equation, the complete ionic equation. The H plus, the HBr breaks into ions, and the potassium sulfite breaks into ions. The water doesn't, the SO2 doesn't, the KBr does. And so we end up with potassium ions and bromide ions on both sides, and so I just rewrote the equation without them. Any questions? Fun, right?